In today's lesson, we're going to look at the integral of x to the power of e plus e to the x plus e to the e with respect to dx. We'll look at some other ones as well. Let's start off with this one here. So when you're taking your integral can act linearly on each one of these separately. So I can write this as the integral of x to the e dx plus the integral of e to the x dx plus the integral of e to the e dx. Now, if you take a look at our first one here, this is just your power rule applied. If I go to take the integral of this, I need to think of a function whose derivative is going to be x to the power of e. Well, if I look at x to the power of e plus 1, if I go to take the derivative of this, power rule says I drop down the e plus 1, subtract 1, I'll get that power of e that I want. The only issue is I'll have a coefficient of e plus 1 in the front, which I have to get rid of. So I'll divide by e plus 1. Moving on to the next one here, e to the x is the derivative of itself, so this will just be e to the x. And lastly, e to the power of e is just a constant term, no different than 2, 3, 4, anything like that. So the derivative of e to the e times x will end up being exactly e to the power of e. And I'm going to go ahead and add a constant term k here. All right, let's take a look at another example. So in the next example here, we have the integral of x cubed plus 3x plus 4 all divided by... What you want to do is you want to kind of be in a situation like above where you can break this apart, as I did in the previous example, into simpler terms here. So I'm going to go ahead and do that because you can break this up as the integral of x cubed over root x dx plus the integral of 3x over root x dx, and lastly plus the integral of 4 over root x dx. So now that you're in this situation here, taking the integral of just a basic exponential, this will be x to the, again, this root of x, I can rewrite as x to the half, so this will be 3 minus a half, in which case you're going to get x to the power of 5 halves dx plus the integral of, I can pop that 3 out, and this will be x over root x. I'll be left with just x divided by root of x. So this is just going to be x to the power of a half dx. Plus, again, I can pop this 4 out over the integral of x to the negative 1/2 dx. So now I'm breaking this up in terms of the integral of a base, in this case of x, to some real value, each one of these. So taking the integral of this is quite easy. This ends up being the integral of this is, again, I need to think of something I take the derivative of. That'll give me x to the power of 5 halves. So if I look at x to the power of 7 halves, you subtract that 1, and when you drop down the 7 halves, you'll get your 5 halves that you want. But again, I'll have a 7 halves in the front I want to cancel off, so I'll put a 2 over 7 in there. Likewise, using the same strategy here, I can change this to be x to the power of 3 halves. And when I go to take my derivative here, I can drop this down and write this as 2/3. And I can write this as x to the power of 1/2. And I can pop a 2 out front here, plus some constant value k. So this becomes 2 over 7 x to the 7 halves plus 2x to the 3 halves plus 8 x to the half plus k. All right, let's take a look at our last example here. So for this example here, we want to take the integral of dx over root x times 1 plus x. So in this situation here, notice we can't do the same technique where I kind of break this up into a sum of integrals separately, kind of breaking this up. We can't do that because all the variables are in the bottom, so I somehow have to get to the top. I'm going to go ahead and do a substitution here. I'm going to let t equal the root of x. And you notice right away, once I do that, this will end up being equal to x to the half. So dt is going to be 1/2 x to the minus 1/2 dx. In other words, 2 dt is going to equal dx over the root of x. So you can see I can replace the dx and the root of x. I can replace that with a 2 dt. Definitely making this quite easier. And now I can go ahead and continue this idea if t equals the root of x, that means that t squared plus 1 will equal 1 plus x. So I can go ahead and replace the 1 plus x with a t squared plus 1. And let's see what we have now. So if I do that, this will be the integral of 2 dt divided by 1 plus x is just going to be 1 plus t squared. So now if we take a look here, we're taking the integral, let's move this over here, of 2 dt over 1 plus t squared. I can pop that 2 out. We now have the integral of dt over 1 plus t squared. But we know that's exactly equal to the tan inverse of t plus some constant value k. And in this case here, I know that t is equal to the root of x plus k. And then we have our integral once again. So the integral of dx over root x times 1 plus x ends up being 2 tan inverse of root x plus k. Okay, that's it there. I just want to do a couple quick sort of basic examples of integration. Thank you.